Hello everyone, today we are going to discuss power series method in differential equations. See section 8.1 and 8.2 in your textbook. I'm going to start with power series reminder. If you remember very well what is power series from a calculus course, then you might wish to skip this video and switch to the next one about the method itself. So what is power series and what is Taylor series? Power series is the expression like that. You just write this down. You can write this as a sum or write out several first summands. A0, A1 and so on are constants. X0 is also the constant one and the same, called they say that this power series is centered at X0. And then X is a variable. Now, each power series has its own radius of convergence. This series converges when x minus x0 is smaller than r and diverges when it is larger than r. When x minus x0 is exactly r, the absolute value of x minus x0 is exactly r, then the series might converge or might diverge. So that's how convergence and divergence of this series looks like. This radius of convergence can be 0, which means that this series never converges except when x equals x0, which is trivial because all the terms are 0. And r can also be infinity. This means that the series always converges for all x. Or it can be something in the middle. So we mostly talk about power series that represent functions. To discuss this, I'll need to remind you what is Taylor series. For most functions, you can write this. For many functions, you can write this. Fx equals this infinite sum. These are derivatives at some point x0. This whole thing is power series, and these are its coefficients. This power series is called Taylor series centered at x0. This formula doesn't always work. It just works for some functions that are called analytic functions. So even if the Taylor series can be undefined. If the function is not infinitely differentiable, then this term can be undefined. Or this series can diverge everywhere, or it can converge to your own function, but for good analytic functions, this formula holds true. Near x0. Near x0, this formula holds true for x minus x0 sufficiently small. So we are only going to work with analytic functions. Now, if you know the infinitely differentiable function, you can easily, you can write out the right-hand side. You can write the Taylor series. To do this, you just differentiate this function at x0 and compute derivatives and substitute in the formula. So from now on, we set x0 to 0 and only consider series that are centered at 0, just for simplicity of notation. You can also apply this or the theory to the series centered at any point. But let x0 be 0, so you only have ak x to the power k here and x to the power k here. First of all, I'll list several Taylor series. You probably know the Taylor series for the exponential. We used it when we defined matrix exponentials. This is the short form. The general term is x to the power k divided by k factorial. And the series converges for all x, and for all x you have this. So the radius of convergence is infinite, and for all x you have this formula. There is also a series for sine. To remember the formula, you should remember that you keep odd terms from this formula only and alternate signs. This also converges for all x. The formula is true for all x. Now this is a formula for cosine. now you should take this formula for the exponential and keep only even terms and alternate signs. That's how you can remember the Taylor series for cosine. I'll also explain why we have these formulas a little bit later. Why do we have this relation of these two Taylor series? One more thing is Taylor series for logarithm. So you don't have factorials here, you just have 2, 3, 4 and so on. This logarithm is of 1 plus x. This is on purpose. I cannot write x here because when x is 0, logarithm of x is not defined. So I write 1 plus x here. Now this is yes, and the series for logarithm only converges when the absolute value of x is smaller than 1, because otherwise the logarithm of 0 is undefined, so this cannot hold true when x is greater than 1. The absolute value of x is greater than 1. Okay, now this formula is one more Taylor series for 1 over 1 minus x, and is actually a formula for the sum of the geometric progression. The right hand side is a geometric progression. When you sum it, you get 1 over 1 minus this x. This formula also holds true when the absolute value of x is smaller than 1, otherwise the terms over here will tend to infinity and the series will not converge. And you can generalize this formula to 1 plus x to the power alpha. I will not comment this, I just included it for completeness. There are also series for tangent, for cotangent, for arctangent or whatever. They are more complicated, I'm not going to list them. To obtain all these formulas, you just take your function and differentiate it and substitute 0 in your derivative, so this gives your coefficients in these formulas. Now, why do we need power series? Because they are easy to operate with. So I'm going to show you how to work with them. What can you do with power series? You can add and subtract them. This is kind of trivial. I added sine and cosine, and this is their power series that represents the sum. So this is also a Taylor series. This is a Taylor series of this function sine plus cosine. I don't need to compute its derivatives. I just use the sum of the series for sine, the odd terms here, and the series for cosine, the even terms here. So it is easy to add and subtract power series. You can also multiply them. So suppose you want to multiply this series of 1 divided by 1 minus x by itself to get the Taylor series for 1 divided by 1 minus x squared. So you take the series for this function, multiply it by itself. To multiply Taylor series, to multiply power series, you just open brackets. So you get 1, then you have x and 1 more x, you get 2x, then you have 3x squared and so on. You can easily see the pattern here, so the coefficients are 1, 2, 3, 4 and so on. This is the Taylor series of this function. That's how you can obtain it without remembering it. One more thing you can do with power series is substituting. For example, how can you compute the Taylor series of e to the power x squared? You just take the Taylor series for e, and instead of x you substitute this x squared there. And this is a general rule. You can also compute the Taylor series of sine of x cubed or whatever. You should use a little bit caution here. For example, suppose I want to substitute 5 plus x in the series for 1 divided by 1 minus x. Then I just do this. I just write out this expression. And this will be true if this 5 plus x is at most 1. So this formula will be true only if 5 plus x is where it should be, in the domain of convergence. One more issue with this case is that the right hand side doesn't have the form of power series centered at 0. It is kind of centered at a different point. You don't have x, x squared, and so on. You have 5 plus x, and so on. It is centered at the wrong point. But still, the formula is correct. What else you can do with power series? I wanted to show this. You can use complex numbers. All the theory about power series extends to the complex case and complex analytic functions. This is one of possible foundations of complex analysis. You can do everything with complex x. For example, this shows you another way to prove the Euler's identity, that e to the power ix equals cosine plus I sine. If you just take the series for the exponential and substitute ix in the series, that's what you get. Then you separate away real terms from imaginary terms. When you compute I squared, it gives you -1, so it is -1 over here. I to the power 4 is just 1, it is 1 here. So the even terms give you real terms, here they are. And complex terms are odd terms, here they are. So if you do this, you get series for cosine plus I series for sine. These are algebraic operations with power series. Now, why we love power series? Because the analytic operations are also simple. Integration and differentiation is rather simple. So, first of all, if you have power series, you can integrate it term-wise. You take your power series inside the integral. Oh, sorry for the misprint. This summation should be at the sum, not at the integral. So you should move this k here to the sum. Sorry for that. Yeah, I'll fix this in the slides when I upload. So you can integrate this sum term-wise. To do this, you just integrate each term. That's what you get when you integrate each term. C is because the integral is indefinite, so it is c plus arbitrary constant plus this function. Say, for example, you can obtain the Taylor series for logarithm without remembering it, because logarithm is the integral of 1 over 1 plus x, and then you replace this by its series. It is geometric series with minus x instead of x. So this is the Taylor series of this function. Now you integrate term-wise, you just integrate each term. That's what you get. This is Taylor series for logarithm. You can also figure out that c is going to be 0, because when you just substitute 0 in logarithm, you get 0, and when you substitute 0, if you substitute 0 here, you get logarithm of 1, which is 0, and then when you substitute 0 here, you get c, so c is 0. This is actually one more important idea, that when you have power series and substitute 0, what you have is your free term. What you get is your free term. That's how to integrate power series. You can do this whenever you are inside the radius of convergence, whenever the series converges. And you can also differentiate term-wise. You just differentiate each term. X to the power k, its derivative is k x to the power k plus 1. I started the summation from 1 here, because when k is 0, this term is 0 anyway, and also because the free term is just a0 and its derivative is 0. So I started the summation from 1. For example, there is another way to compute the Taylor series for this function. We did this on the previous slide by multiplication this by itself, but you can also write this as a derivative of this function, and then you write out the series for this function, differentiate it, and that's what you get. This is actually a simpler way than to multiply this by itself and open brackets. So you differentiate this series, you differentiate term-wise, x gives you 1, x squared gives you 2x, and so on. These are analytic operations that you can do with power series. The last thing we will need about power series is that you can shift indices. This is not a true operation, because if you ask me what happens with power series when you shift indices, the answer is nothing happens. So this is the formula. if you have any power series, you can shift the index k by 2 or any other positive number. You can just replace this k by k minus 2. So it means that you change your notation. Instead of this number that changed from 0 to infinity and was over here, you used to denote this number by k, but now this number will be k minus 2. You replace k by k minus 2 in your formula, and you also change the region of your summation, because your new k is the previous k plus 2, so it starts from 2. If you are not sure how to apply this formula, you can just write out your sum in this form. Just write out several first summands, and then let's have a look at the right hand side. When k is 2, then you have a0 x to the power 0. When you have k equals 3, then you have a1x, and so on. So the right hand side is just the same as the left hand side. If you write your series like that, then you do not notice any difference. If you write your series like that in a compact form, then you might have to switch indices. For example, why is this useful? If you differentiate your series term-wise, that's what you get, the formula from the previous slide. And then you probably wish to have x to the power k here, to have a more standard form. Then you can shift your indices by 1, and then your summation starts from 0. This k is replaced by k plus 1, and this k is replaced to k plus 1 as well. That's why you have x to the power k here. What happens to the series on this step? And the answer is nothing. If you just write out the several first terms, they will be identical in both cases. And all the series will be identical. The only difference is which thing do you denote by k. The difference is which thing do you denote by k. This is the last operation we will need for the method. Okay, this was the power series reminder. Now let's have a break. After the break, I will discuss the power series method to solve differential equations.